Here we go. Lately, we have been looking at integrals, both definite integrals and indefinite integrals. And as I mentioned before, a significant portion of Calc 2 is spent on different methods of integration. And that's because it's usually a lot more difficult to integrate than it is to differentiate. And so it takes a lot more time and there's a lot more involved. In this lesson and the next lesson, we're going to look at the first big method of integration, or the first big rule of integration. And this is going to help us evaluate integrals of compositions of functions. Let's take a look at a classic example. We are going to evaluate the integral of 2x times the square root of 1 plus x squared dx. Now, unfortunately, we do not have a nice formula for the antiderivative of this function, so we're going to need a new tool. And in this case, that tool is going to be a new variable. Now, if you look inside that square root, if this was just the square root of x, that wouldn't be a big deal, but it's the square root of a whole other function, 1 plus x squared. And so to simplify things, we're just going to replace 1 plus x squared with a dummy variable, which we're going to let be u. So let's let u equal that inner function, 1 plus x squared. Now, here's the thing. We're going to try and make a substitution. We're going to try and go from x to u. But the thing is, we are having to integrate with respect to x. That's what that dx means. But we are able to go from dx to du if we can have a relationship between dx and du. And the way that we get that relationship is by differentiating the equation that we used for our substitution. So if we differentiate this with respect to x, the left-hand side is going to be du over dx, because that's what it means to differentiate u with respect to x. And then on the right-hand side, the derivative of 1 is nothing, and then the derivative of x squared is 2x. So by differentiating that implicitly with respect to x, we end up with du over dx is equal to 2x. And what we're going to do is we're going to write this a little bit differently. We're going to take that dx that's in the denominator, and we're going to move it over to the right-hand side. I know that's not really a fraction, but we're going to treat it like it is for a moment. And we've got du equals 2x dx. And we call this a differential, and this gives us a relationship between du, which is a small change in u, and then dx, which is a small change in dx. And this is going to allow us to switch everything over from x to u. And you'll even notice something really useful in the integrand. We have a 2x dx here, which is exactly what du is equal to. So what we can do is we can replace that with du. So this integral is going to be equal to, if we look at the square root of 1 plus x squared, remember we said that 1 plus x squared we're going to let be equal to u. So that means that's going to be the square root of u. I can actually color the other one in as well. We're replacing that 1 plus x squared with u. And then the 2x dx, that's the rest of it, we know that is equal to du. So that's just going to be the square root of u du. Now, I said I was going to give you kind of a very classic example for the substitution rule. This is a classic example because when we took the derivative of the inside, 1 plus x squared, the derivative that we got, 2x, was in the integrand. And so we were able to take that 2x dx and replace it with du. There are other situations where that's not going to be the case, and we either have to be creative or substitution isn't going to be the right method there. But in this case, We needed that 2x to be there for us to be able to make this substitution. If it wasn't there and it had just been the square root of 1 plus x squared dx, we wouldn't be able to do the substitution because we wouldn't be able to convert the dx to a du without having any extra x's. When we make this substitution, we need this new integral to be everything in terms of u. Now, once we've done that, we can use the fundamental theorem of calculus to find the antiderivative. This is the same as u to the 1/2, and we know that the antiderivative of that, or the integral of that, is u to the 3/2 over 3/2 plus a constant. Now we know that dividing by 3/2 is the same as multiplying by 2/3, so this is the same as 2/3 u to the 3/2 plus a constant. But we cannot leave our answer like this. Can you see why not? Well, we were originally integrating a function of x, so we can't have our answer be a function of u. We need to go back to x, and so we go back to the substitution that we made, and wherever we see a u, we're going to replace that with 1 plus x squared. So in the end, this is going to be 2/3 times the quantity 1 plus x squared raised to the 3/2 plus a constant. Now, if we want to check if this answer is correct, remember, we can always check an indefinite integral by differentiating the result and seeing if we get the original integrand. So let's go ahead and check our work here. And we can do that by differentiating the new function, 2/3 times the quantity 1 plus x squared to the 3/2 plus a constant. If we want to differentiate that, well, the derivative of a constant is 0, so we can ignore that. In the first term, we've got that 2/3 there. And then, if we want to differentiate 1 plus x squared to the 3/2, we're going to have to use the chain rule. We start by differentiating the outer function, which is raising this to the 3/2. And the derivative of u to the 3/2 is 3/2 times u, which in this case is 1 plus x squared, to the 1/2. We subtract 1 from the exponent. And then we have to multiply by the derivative of the inside. The derivative of 1 plus x squared, well, the derivative of a constant is 0, and the derivative of x squared is 2x, so we've got that. We see that the 2/3 and the 3/2 end up canceling. And so in the end, we put that 2x out front, and we know that raising something to the 1/2 power is the same as taking the square root. So we have 2x times the square root of 1 plus x squared, and that is exactly what we had in our integrand with the dx. So we know that we integrated correct, because when we differentiate the result, we get that integral back out. And we call this rule the substitution rule, because that's exactly what we're doing. We are making a substitution. And I'll give you that rule here. The substitution rule for indefinite integrals says that if u equals g of x is a differentiable function whose range is an interval I, and f is continuous on I, then the integral of f of g of x times g prime of x dx is equal to the integral of f of u du. Basically, we have to have a composition of functions where the inner function has its derivative in the integrand as well, which is what we saw here. We had a composition of functions, and the inner function 1 plus x squared had its derivative 2x also in the integrand. Now, we need these functions to be continuous, and we need the inside to be differentiable because we take the derivative of it in this process. But so long as those things are met, we've got no problems, and we can use this. I'm going to make another video on this topic because I mentioned that this is kind of the most classic example There are some that are a little bit more difficult, that require some manipulations or some creativity, and we really need to get some practice with that. This is not the sort of thing that you can look at one example and all of a sudden be an expert on. You really want to get a lot of practice with these.